Thank you all for coming today. Today I'm presenting a preliminary case study of forest soil development following industrial disturbances. So I emphasize the preliminary part because I don't think I'm going to be giving you so many answers as much as perhaps raising more questions and thought for future work. This was very much an exploratory piece of work that we conducted last summer in order to try to better understand some of the soil physical changes after different types of industrial disturbances. I'm going to be speaking today a lot about compaction, so I thought I would quickly define it and mention a couple of the methods that are used for the measurement of compaction. So Rooney et al. Have a nice definition of it, so I kind of borrowed their definition. Soil compaction may be generally defined as an increase in the natural density of soil at a particular depth. This density increase translates into less available pore space, less available plant water, slower water transport, and a decrease in plant roots' ability to penetrate the compacted zone as it tries to seek out water and nutrients. We use measures of bulk density, penetrometers, and then therefore penetration resistance, and also visual assessments may be used to study compaction. It's been suggested that in reclamation, decompaction may often be necessary to restore hydrological functioning to well sites or other similar industrial disturbances that have been operated on. I'm not sure if I personally agree with this or not, but that's been the general thought, at least in the Northwest. Now, susceptibility to compaction itself is often site-specific and can be driven by inherent differences in soil texture and moisture at the time of compaction. So in the Northwest, we have generally fine textured soils. Therefore, in this region, they are very susceptible to compaction because finer textured soils tend to be more susceptible to compaction than coarser textured soils. However, from an operational standpoint, we can't necessarily run around and decompact the whole Northwest. It's costly, and it may not always be necessary, and in certain cases it has the potential to do more harm than good. Now, soil compaction is not the only factor limiting reclamation success. There's many things that will influence whether you end up with a field of grass or a nice regenerating mixed wood, or it could be pine forest or what have you. Soil nutrient availability, soil moisture, climatic conditions at the time of revegetation are all also playing a role. And that's just further emphasized here. So plant performance on reclaimed sites is factored in by a number of variables. Today, the disturbance types that I'm going to be focusing on are disturbances as a result of forest harvesting operations and disturbances as a result of oil and gas activity. So for the forest harvest disturbances, I'm focused on chip deck landings. In the area I was studying, DMI, or Dietschel Marabini, is a pulp mill in the region, and they actually bring a chipper on site to chip the aspen for their pulp mill. So this is a pretty heavy disturbance. It severely compacts the soil. And of course, I think we're at least somewhat familiar with oil and gas activities. So sump sites, borrow pits, well sites are all heavily trafficked areas. That's the common feature between both of these, is the trafficking. But the main difference is the level of disturbance to the soil. In oil and gas activities, we are stripping the topsoil and storing it, and in forest harvesting activities, we tend not to do that, or have no necessity to do that. So I have two objectives for this project. And the first is to quantify soil bulk density following the use of common decompaction treatments, and compare these treatments to both untreated sites, so disturbed but had not been treated with any decompaction methods, as well as undisturbed soils. So these are natural forest soils. And I also wanted to quantify the differences in soil physical properties, or bulk density is what I focused on today, between these different types of disturbances. So this is just a table summarizing the sites I'm going to be talking about today. So there was 4 sites in oil and gas disturbed areas. I'm going to often call them well sites, but this does encompass burrow pits and sump sites as well. And so 4 of these sites had been plowed in 2008 and then planted the following spring. And then we also looked at 4 oil and gas disturbances that, or 4 sites that had not had any compaction or decompaction treatments done to them. And they ranged in age from 0 to 10 years old. And then we looked at 3 chip deck landings that had been ripplowed, and 3 chip deck landings that had wing shank, which is another type of plow, and I'm going to explain that next. And then we also, can't forget, looked at the adjacent forest in these particular sites as a benchmark. So the rip plows was mentioned earlier today in Pam's talk, and so this is a deep ripper or subsoiler. It goes fairly deep into the soil profile and lifts the soil profile. The principle is that water and ice and snow are going to get in here and actually do the decompaction for us. So the freeze-thaw events are going to break up these big clods and actually get into the lower profile so that we have a decompaction effect much deeper than the surface, and that's often found with other methods, is that they don't go deep enough. So that's the main principle of this method. So you often have 2 shanks in parallel, and he does lapping passes so as not to run over the already decompacted soil. The wing shank is a slightly different implement, and it's just a modification of a straight shank, or well, wing shank or modified shank, and it's just got a wider wing tip here, and it's supposed to do a similar thing. It's supposed to lift the soil, but it tends not to be so aggressive, so you don't have these big, huge, or necessarily have these big, huge clods of soil. It looks a little less obtrusive. So DMI was hoping that they could get away with using this versus a more aggressive subsoiler. So I'm just going to show a few visuals now of the sites that we worked on. So these are the non-decompacted well sites. So there is actually regeneration on all of the sites that we were working on. These are the rip-plowed sites. These were historic sites that had already been rec-certed. DMI had gone in 2008, as I mentioned before, and plowed these sites. They had nothing for real forest regeneration. They were essentially grass fields. So they thought, well, let's go in, decompact them, because that's generally the thinking, is that compaction is the reason we're not seeing any tree growth, and then plant them with white spruce. And this was, I'd have to say, for the white spruce, largely unsuccessful, but that's probably for another talk. And then these are the landings that we worked on. You can see the border here. This is in the fall, so the aspen has lost its leaves already, but this is the aspen and the cut block there, and then this is part of the landing here. This is the landing border right here, and then you can see the white spruce growing along here. And one of the summer students happily digging soil pits and collecting bulk density. And because this is a soils conference, I thought I should at least show a couple of soil profiles. And so the first one here is just a profile of one of the rip-plowed landings. And I want to highlight there's a nice layer of organic topsoil here, or forest floor material. They actually had pushed the forest floor material aside when they plowed, and then put it back on afterwards, because they found that all of the coarse woody material kept getting hung up in the shanks. So it was put back in place after. And in comparison to this really awful picture of a hole we dug in one of the well sites, and there is no organic topsoil in the same way that it is here. It's an admixture, and this is pretty common, at least in the region I've been working in. The topsoil in general is quite thin. These big cats can't help but mix the lower mineral soils with that organic topsoil, so what you always end up with is sort of an admixture in the top horizons. Methodology is going to be really fast because we only did a couple of things. So we used a penetrometer on the forested undisturbed areas and on the well sites. We didn't do any penetrometer work on the landings. We simply ran out of time. And we collected bulk density samples on all of the sites that we worked on. And wherever we did penetrometer work, we used a TDR probe to assess soil moisture, because penetration resistance is tightly coupled with soil moisture. All of these samples were taken on a spatially explicit grid. We are actually working on looking at spatial changes in bulk density and soil resistance, but we don't have any data to present on that yet. So into some data. I'm going to kind of walk you through graph by graph here. All of the data presented has 95% confidence intervals, and that's the long bar. And then the smaller bar with the crosshatch are LSDs, or least significant difference intervals. And these give us an approximation of what sort of statistically different between means at a p-value of 0.05. It's a guideline more than a cutoff, in my opinion. So I use this as a visual guide to see what's kind of going on with the different treatments that we employed. So the first two bars, the reddish-brown color, are the landings. So the first one is the modified shank or wing shank. The second one is the ripplowed. And then we're into the two wellsite types, so the ripplowed wellsites, and then the non-plowed wellsites, and then the adjacent forest. And you can see here that in the top 5 centimeters, there's clearly a difference between both well sites and then the rest of the treatment. So the forested sites are much lower, and the forested sites are very similar to what we see in the landings. This is largely driven by differences in soil texture. Recall the soil profile I showed you. It was quite organic. There was a lot of organic material in the top layer. There is organic material in the top layer in the forest site. There's nothing in these ones. So that's driving a lot of the difference we're seeing here. I'd also like to highlight the difference here. Statistically, there is no change between the plowed and the unplowed well sites, but there is definitely a trend down. So the plow does seem to have some effect after 4 years. So this soil has settled out quite a bit in this time. And for those that went to the earlier talk, they did see fairly large changes in plowed versus unplowed soil, but that was only a year after disturbance. As time goes on, we expect some of that soil settling to occur. But there is still something of a change here, and this change could probably equate to very large changes in available pore space and water infiltration for plant growth. As we go deeper into the soil profile, we see a lot of the differences here are disappearing. So, the well sites are virtually, to all intents and purposes, identical, and then the landings and the forest soils are running up to that 1.5 or so level that we see in the well sites. And then by 30 centimeters, they are virtually unchanged. In terms of soil resistance, the story is similar and even less different. The surface soil resistance is less than the deeper soil layers. That's not a huge surprise, but there is virtually no change in the forest and well sites compared, there's no difference between the forested sites and the well sites. In the surface and the deeper layers, there almost seems to be a trend towards higher soil resistance in the forested sites, but I would suggest that this is largely driven by differences in soil moisture, and we'll see that in the next figure here. Soil moisture in the forest was on average drier than in both well site types. This is not a huge surprise. We had a very dry summer this year, and canopy interception is going to further reduce that, and greater evapotranspiration in the forest relative to these open sites. So that's probably largely what's explaining this little blip up here. And that's sort of further supported by the Pearson correlation coefficient at that lowest depth. So there is some correlation between soil moisture and soil resistance. Although we need to take this with caution because the TDR probe was integrating soil moisture over 0 to 12 centimeters, and this is soil resistance at 20 to 30. So the exact interpretation on that is sort of questionable. I guess I haven't run out of time yet, so I can speak a couple words about the vegetation, and the vegetation as it pertains to the well sites that were plowed versus the well sites that were not plowed. The vegetation here, in terms of woody vegetation, was terrible, to be honest. I think it was either a combination of, because it wasn't bulk density or compaction per se, it was a combination of competition with grasses. When you decompact a site, it's not just good for trees, it's good for everything else. Or there may be secondary soil chemistry issues. This region has saline soils, and in some of our other work, we're seeing moderate salinity across many of these well sites, and decompaction actually seems to increase EC from what we're seeing. So this may factor into why we're seeing lower woody density here. Without intervention, no decompaction, no nothing, we're seeing very good stem counts. Why this is? I don't know. Nothing was done here. It's kind of hit and miss, right? And that's sort of part of why we're trying to go out there and explore a little bit about what's going on in the soils, is to try to understand why do we get great stem densities when we do nothing, even under moderate compaction, and then we run around and send a plow out there and we still are unsuccessful. And that's sort of further, I just show a few pictures here. So these are the non-decompacted well sites, and this is why I show white spruce because it was common to all of these locations. So it's pretty healthy, happy little white spruce. The well sites, it's not that happy. It's on its slow way out. Conifers have a nasty habit of actually living for a number of years before they die. And then these are the spruce on the landings, and they're doing fairly well where we can see them. So in conclusion, the modified shank and rip plow on landings showed similar ranges of bulk density across soil depths and were comparable to forested sites. However, on well sites, the rip plow actually may have some utility in reducing bulk density in the upper soil layer. This is an important soil layer. Many of our fine roots are in the upper 10 centimeters, so this is not something we should discount, even though it was a small change. However, at deeper soil layers, there's very little change in bulk density or soil resistance, and this may be a good or a bad thing. It suggests that whether we disturb the sites or not, whatever disturbance we do and subsequent plowing we do, we are converging towards a natural system, at least in this parameter. And I just want to say thanks to our summer field staff, Florence, Peggy, and Doug for site location assistance and funding organizations.